Hi everyone, this video will run through the adjacency matrix in the context of networks and decision mathematics in further maths. An adjacency matrix is that tabulated representation of the direct connections. So from our matrix unit or our matrices unit, we know that we were able to show connections between the different points or the different vertices in our graph. And so a couple of things to note here. We have our graph and each of our vertices are labelled. And in this case, we have 4 vertices in this graph. So that means my matrix will be a 4 by 4 square matrix. So we take the labels and generally speaking, we put them in alphabetical order down the side. And then we follow that same order to label our columns. And so then if we were to look at this first row K, what we're showing in each of those positions, so in row K, column K, is there a direct connection from vertex K to K? Now that would only occur if there was a loop. Okay, so a loop would need to occur for us to put a value there. If there is no direct connection, then we record that as a 0 in our matrix. But then as we work our way across our row and we're showing the connection from K to L, we can see that yes, we do have a connection and there's one edge showing that connection. So we put a 1 there. K to M, there is no direct connection. K to N, there is again one single edge there. If we had a multiple edge, so let's say from N to M, there was actually 2 edges, a multiple edge. So when we're representing that in our matrix, if we look at M has no direct connection to K. It has no direct connection to L. There is no loop at M, so again we put a 0, but there is 2 edges connecting M and N, so we represent that there. If I go back to L, so L to K, there is one connection. L to L, there's no loop. L to M, no connection. L to N, there is one edge connecting there. And finally, if we look at vertex N, so N to K, there is one edge. N to L, there is one. N to M, we have 2 edges there. And N to itself, there is no loop, so a 0. So when we look at our adjacency matrix, something to acknowledge is that if we look down our leading diagonal, firstly, our leading diagonal will show us if there are any loops. So if there was a 1 or a 2, that would indicate how many loops there are there. Each loop is only counted as one direct connection. So it's one edge connecting that vertex to itself. Then the second thing we need to understand is that this is actually a symmetrical matrix. So if we look at the upper triangle above this leading diagonal, it is a mirror image of the lower triangle below the leading diagonal. By the same token, something in row 2, column 1 will have the same value as row 1, column 2. So swapping that row and column reference value. We're now going to have a look at some common exam questions that utilize adjacency matrices. And you'll note that in a lot of the examples, it is going from a matrix version to matching it to a graph. And the other way is from the graph matching it to the matrix. These types of questions tend to come up in exam 1, multiple choice. So it's about how can you limit or narrow down the options that you need to consider as correct answers. So first example here, the matrix below shows the number of road connections between town F, G, H and I. Which of the following graphs shows all of these road connections? First thing I would be looking at is this leading diagonal. So remember, our leading diagonal will show us if there are any loops in the graph. And we can see from that there is a loop at G. So if we look at our answer options and check which of them, if any, do not have that loop. So A, we can see there is no loop there at G, so that is not a correct option. B has our loop at G, so we can leave that as an option for now. C, again, we have that loop at G. D, no loop, so we can knock out answer D. And E, again, has our loop, so we'll leave that for now. The second thing I then look for in the matrix, is there any multiple edges? Remember, our multiple edges are shown by values that are not 1. 1 represents a single edge, but in this case, that 2 represents that there are multiple edges between G and I. So again, checking through the options that we have on our graphs left, option B, there is only a single edge between G and I, so we can say B is not our answer. C, we do have multiple edges. We've got 2 edges running from G and I. And E, G and I, again, we have 2 options there. So now that we've got it down to 2 possible options, there's a number of different processes you can undertake now. So we could either just check the connections that we can see in the matrix, do they exist in the graphs? The other thing that we could do, if we consider the row total, that is actually giving me the degree of that vertex I. So for example, I am saying that in this row, I have a total of 3. So I has a degree of 3. And when we look at our 2 options left, in option C, vertex I has a degree of 4. Whereas in option E, vertex I has a degree of 3. So that leads me to say that my best answer is answer E. Obviously, you can, as I said, go through and check the connections. So F should only have a connection to H and I. And we can check each individual one as we go through the rest of the matrix to help you work out which is the best answer left. The next question here is stepping up slightly. So going, instead of just straight matching, we're now looking at a graph and a partially filled in adjacency matrix. So here we have obviously just the leading diagonal drawn in for us, and the rest of the elements are missing. And the question is stating that the adjacency matrix contains 16 elements when complete. Of the missing elements, 8 are 1s, 4 are 2s, and so on. So we have a number of options. So here, one way of approaching this would be a bit of guess and checking, but I think probably the most efficient, because it's not an overly complicated graph, is simply just to go through and complete the adjacency matrix that we've been given. Okay, so they've actually given you the challenging, the difficult ones where the loops, that's where people make the common mistake. But if we were just to read across row W, so we're looking at vertex W and the connections that it has. So our loop has already been shown in the matrix. W to X, we can see there are 2 edges connecting there. W to Y, again, we have 2 edges connecting there. And W to Z, we have a single edge connecting. Now if we move on to row X, so we're concentrating on vertex X, X to W, again, those same 2 edges connecting back. X to Y, we have a single edge there, so 1. X to Z, again, a single edge there. Y, so vertex Y, connecting to W, we have 2 edges. Y to X, we have that single edge. Y to Y, there's no loop, so 0 is already shown. Y to Z, again, 1 connection there. And finally, vertex Z, so Z to W, we have 1. Z to X, we have 1. Z to Y, we have 1. and the loop at Z already shown. So now of the missing elements, so just the ones we filled in, we have 1, 2, 3, 4 2s. So 4 2s. And we have 1, 2, 3, 4, 5, 6, 7, 8 1s. So option A is our best answer there. Obviously, you can choose to fill out one diagonal of that, or sorry, one triangle, and use the property that it is symmetrical and work it out from there. But sometimes it is just quickest to run through the whole thing. This next question, we're just supplied a graph and some information. So the friendships between 5 children are summarised in the graph to the right. The vertices A, B, C, D and E in the graph represent these children. Each edge between the two vertices indicates that the children are friends. For example, the edge between vertex B and vertex C shows that child B and child C are friends. An adjacency matrix that summarises the friendships can also be constructed. In this matrix, a 0 indicates no friendship and a 1 indicates a friendship. How many 0 elements will there be in this adjacency matrix? So how many of the spaces will be filled with a 0? So how many non-connections? So one option would be to construct the adjacency matrix and count up the number of zeros you have. But if we want to take it a little bit further and think about, well, what is known here? But without drawing the adjacency matrix, what can I draw from or identify from the graph that I have? So we can see here there are no loops. So no loops means that the leading diagonal will all be zeros. So that is 5 zeros that will occur down that leading diagonal. The second thing we can see is that obviously if we look at A, vertex A, there will be a 1 connecting to B and a 1 connecting to D, but there will be a 0 to C and E, meaning that vertex A will have 2 0 elements in its row A. So there'll be A will have 2 zeros. Vertex B is connected to all of the other vertices. It has 4 edges leaving it. So there'll be no zeros there. Okay. Vertex C, again, only has a degree of 2. So there'll be a 0 in its connection to A and a 0 in its connection to E. So C will have 2 zeros. D is connected to everything else. And finally, E, again, a 0 to A and a 0 to C. So E, 2 zeros. And so that means when I add up these values, I actually have 11 0 elements altogether. And so that gives me my answer of E. Now, as I said, you could have just drawn the adjacency matrix, but this is just giving you another way to approach this type of question. The next question looks straightforward in that we are given a graph and we're asked to match that to the adjacency matrix. But sometimes the way that these graphs are drawn can be challenging, and so it can be easy to miss some of the information contained within them. So here we have the map shown below showing all road connections between 5 towns, P, Q, R, S and T. The road connections could be represented by which of the following adjacency matrix. So the first thing, again, we want to think about what are those key identifiers? What are the things that are different? And so if I look at my graph, can I see any loops? And it is not as obvious in this format as in sort of the more simplified version of graph drawing. So thinking about, can I leave a town, travel on some roads and get back to that town without going through another one? And I can see here at town P, I can leave and come back by not crossing through another town. So I know that P has a loop. So when I look at my leading diagonal, I want to see a 1 in that first top right corner where I'm looking at P joining to P. And so by looking at that first, I can say A, B, and E contain that element, but C and D do not. So we can eliminate those two options. And so then we can revisit our graph and check if there are any other obvious loops, or looking at the options we have left, the only version that has a second loop is in E, where there is a loop between S and S. And so we can check on our graph, there doesn't appear to be a way to leave S and not pass through another town without and return. So we can also eliminate option E. So then our next step might be, let's look at some of the differences between A and B that we have there. And so we can see one of the key differences is this connection from P to Q. In A, we have 3 connections, but in B, there are only 2 connections. So let's consider how we can get the different ways that we can get from P to Q. So there's the obvious straightforward way across that edge at the top. We also then can travel down and straight up. But also finally, a third version might be we travel down and around the other way of that loop. So there are actually 3 different ways of getting from P to Q or from Q to P. So that gives us confidence in saying, well, A is our preferred answer there. But the difficult thing is the way that the graph is represented. So it's taking the time to check those key things and thinking carefully about them. Our final example is another version of using those difficult to read graphs, but this time we're going from the adjacency matrix and matching that to the best version of the graph. So the adjacency matrix below shows the number of pathway connections between 4 landmarks, J, K, L, and M. A network of paths that could be represented by the adjacency matrix is, we've got our options there. So again, we're going to use a similar technique, but work in reverse. So this time, if I look at my adjacency matrix and I check the diagonal, I can see that I need a loop at J. And so if I look at my 5 options, I can see in A, I can leave J and return. So I have a loop there without crossing through another town. In B, there is no way for me to leave and return without crossing through another town. So I can say that B does not provide that loop, so is not an option. C, similar. So I'm unable to leave and get back into J without having passed through one of the other towns on the map. So C is not an option. D, I have this nice little loop here, so I don't need to go through any town to return. And E, same thing. I've got a nice little loop there, no passing through any other towns. So that's looking at the loops to begin with. So I've knocked it down to 3 options. Then looking at some of the other information in the graph. So next up, I'm going to check this single connection between K and L. So I only want one possible edge here. So in option A, I can get K to L, or I could go this way, and that is a direct connection. So that means I've got 2 edges, 2 different pathways to get K from L, so A is not my best answer. If I look at option D, again, I can go from K directly down to L, and let's just make sure that any of these other pathways don't connect, and they don't. So at the moment, D is still in contention. And E, so again, I can go K down to L, and it doesn't look like I can get along any of the other roads between K and L without going through M as well. So again, E is still in contention. So let's now check one of our other options here. And maybe this connection from K to J is our next best one to check. So we should have 3 connections there. So K to J, I need to be able to travel across. So that's 1. K to J, I could come down and up the right side of that loop, or down and up the left side of that loop. So there I do have 3 connections, or 3 ways of traveling from J to K, or vice versa. So let's check the same thing on option D. So I could travel across the top, that's 1. I could come down around my loop here, that's 2. But I'm unable to get any other version or any other pathway from J, without going through either town M or town L. So that gives me option E as my best answer there. And again, the actual maths or the properties that we're looking at there are not difficult, but it is the way that the graph is represented. And quite often they will do that in our exams because they know that they are challenging visually. So it's about taking the time to check those key features and checking those pathways. Okay, that's it for adjacency matrices. See you next time.